Welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and in this video I will tell you about hyperparameter tuning. You should understand the difference between model parameters and hyperparameters. You should know about different types of hyperparameters, and most of all, you should be able to explain the general idea of hyperparameter tuning. Imagine we have a data set and we want to train a classification tree. Before we can train that classification tree, we have to set the maximum tree depth of this tree. So perhaps we did this beforehand on a different data set and feel that the maximum tree depth of 4 would be a good decision. So we decide to set this hyperparameter to 4. What happens now? The learner or the inducer takes the input data, performs empirical risk minimization, and returns a fitted model. So we have here in the middle the inducer or the learner, which takes as input the training data, performs empirical risk minimization, and theta hat is then the arg min of the empirical risk with respect to theta. Usually, we are interested in the generalization performance of the estimated model, so the GE of f hat, which is the generalization performance on new and previously unseen data. So, of course, we do not know the true GE, so that's the reason why we have to estimate it via GE hat. So how do we that? So first, we have the training process from the last slide. As output from the training process, we have a theta hat, which is the arg min of the empirical risk. And then we apply the model to new test data set, the test, and evaluate it on this data set. So here on the slide, you also have the formula, which you will remember from the evaluation chapter. So basically, the generalization performance or the estimated generalization performance is a function of the inducer, of the hyperparameters, of the size of the training data, and of the evaluation measure. So for example, we can say we are interested in the area under the curve. So we estimate the generalization error by the area under the curve on the test data. So we compare the true labels y on the test data with the scores on the test data as well. As a matter of fact, many machine learning algorithms are sensitive with respect to a good choice of the hyperparameters, which means that the generalization performance might be bad if we have chosen a suboptimal configuration. So to illustrate this, we have here on the bottom of the slide 3 plots, one for each machine learning algorithm. We have the decision tree, k nearest neighbors, and SVM, the support vector machines. And we can see the area under the curve on the test data set. So here on the right side for the support vector machine, we have 2 hyperparameters, C and gamma, and right now it really is not important what these hyperparameters mean, but we have 2 hyperparameters, so we can see the best test AUC is somewhere here. And for a decision tree, we plotted the test AUC with respect to the maximal depth. So we can see that in this case, the AUC gets better for trees that have a larger depth. And in the middle plot for the k nearest neighbor, we can see that first, with increasing number of nearest neighbors k, the test AUC drops. But then after, let's say, 13, more or less, it increases again. So it gets better, but in the end, so the best test AUC in this case would be here for k equals 2 or 3, I would say. But it's not a general result. It's just one example for one simulation on one data set. But the important thing is that this could mean that in our example from the first slide, it could be the case that a tree of depth 4 is not a good choice because perhaps the data is too complex. to be modeled by a tree of depth 4, so we would need a higher number of tree depth. Or on the other hand, it could be the case that the data is much simpler than we thought, so a tree depth of 2 or 3 would be sufficient or even better. So what can we do now to remedy this? We can just try out different values for the tree depth, and then for each different tree depth value lambda, we train the model to completion, and then we evaluate its performance on the test data set. So in the plot here, we have in the smaller middle box the training process, where with empirical risk minimization, we train a model given a hyperparameter configuration lambda. And we have again the test data set where we can evaluate the trained model. And what we do now is that we try out different values of this hyperparameter. So lambda 1, lambda 2, lambda 3, let's say a tree of depth 4, 5, and 6. And for each hyperparameter configuration, we train the entire, or we go through the entire training process and through the entire evaluation process. So which means that we have several estimated generalization errors. And then we just take the argmin of those estimated generalization errors. So lambda hat or lambda star would be like the argmin of all those G's with respect to lambda. It is very important to understand the difference between model parameters and hyperparameters. Let's tackle the model parameters first. Those are in our lecture denoted with theta, and they are optimized during training. So they are an output of the training process. For example, for a tree learner, the split points and the terminal node constants are model parameters. And if we are in a linear model, then the coefficients theta are the model parameters. On the other hand, the hyperparameters, which we denote with lambda, are not optimized during the training process. They have to be specified in advance, so they are an input of the training. Those hyperparameters often control the complexity of a model, that is, how flexible the model is, or in principle, they can influence any structural property of a model or computational part of the training process. And the process of finding the best hyperparameters is called tuning or hyperparameter tuning. Examples for hyperparameter would be the maximum depth of a tree, the number of nearest neighbors and the distance measure used in k-nearest neighbors, or in the linear regression model, the number and maximal order of interactions, or for example, the number of optimization steps if the empirical risk minimization is done via gradient descent. Finally, there are different types of hyperparameters. We call, or we summarize the hyperparameters in a vector lambda, which is part of the hyperparameter space capital lambda and can have mixed type. So for example, we have real valued hyperparameters like the minimal error improvement in a tree to accept a split. We have integer parameters like the neighborhood size k for k nearest neighbors. And we have categorical parameters like the question which split criterion should we use for the classification trees. Additionally, hyperparameters are often hierarchically dependent on each other. So this means if, for example, if we use a kernel density estimate for each base, what is the width? So the first step of this hierarchy would be the decision that we use kernel density estimates, and then conditioned on this, we can ask ourselves what should be the width of this kernel density.